Hello students, welcome to Sri Siddheshwar Women's College of Engineering Solapur. We are dealing with unit of partial differential equations and applications. From this unit we will deal with now applications of PDE. As per our syllabus we are having two applications of partial differential equations. The first one is one dimensional heat flow equations, which is given by dou u by dou t is equal to c square dou 2u by dou x square, where c square is the thermal diffusivity of the material of the bar. The second application is two-dimensional heat flow equation in steady state, which is given by Laplace equation, that is dou 2u by dou x square plus dou 2u by dou y square is equal to 0. Now we will understand the concept of the solution of one-dimensional heat flow equation in this lecture. So first consider the equation which is given by dou u by dou t is equal to c square dou 2u by dou x square. Here we are going to apply the method of separation of variables. So we write the solution for u as u is equal to capital T into capital X, where t is a function of t alone and capital X is a function of x alone. Here we want the derivative of u with respect to t of first order and derivative of u with respect to x of second order, obviously the partial derivatives. So let us find these two derivatives. Differentiating equation 2 with respect to x partially, we get dou u by dou x is equal to dx by dx into t. Here obviously t will act as a constant multiplier. And once again differentiating this result, we get dou 2u by dou x square is equal to d2x by dx square into t. Now differentiate 2 with respect to t partially, x will act as a constant multiplier. So dou u by dou t is equal to x dt by dt. Now using results 3 and 4 in equation 1, we get the equation in terms of capital X capital T small t. So here collecting the t's on one side and x on other side, we get equation in this form. Now we are going to equate this with some constant k. This constant k will have three different values. It may be 0, it may be positive real number, or it may be negative real number. So let us discuss three cases separately. First case where k is 0. With k equal to 0, equation 5 becomes 1 upon c square t dt by dt equal to 0 and 1 upon x d2x by dx square equal to 0. Simplifying this, we get dt by dt equal to 0 and d2x by dx square equal to 0. From this, we have to find the solution for capital T and capital X. So we have to integrate these equations. Integrating, we get t equal to some constant c1, and first integration with respect to x gives dx by dx equal to c2. But we want the result for capital X, so we have to integrate one more time this second result. So we get finally x equal to c2x plus c3. Now from these two results for t and x, we can write the solution for u as u equal to t into x, that is u equal to c1 into bracket c2x plus c3. So this is the required solution where k is 0. Now let us discuss the second case where k is equal to m square. With k equal to m square, equation 5 will take this form. Now consider first and third ratio and second and third ratio, so that we can get two different ratios and two different equations. First and third ratio gives 1 upon c square t dt by dt is equal to m square. Now writing this equation in variable separable form, we get this form. Integrating this one, we get log t is equal to m square c square t plus log c4. Applying laws of logarithm, we can write the solution for t as t is equal to c4 e raised to m square c square t. Now let us discuss the solution for capital X. Here multiplying both sides by capital X, we get d2x by dx square minus m square x equal to 0. So this is nothing but the linear differential equation in capital X. So we can write this as d square minus m square x equal to 0, where capital D stands for the differential operator d by dx. Here we can have the auxiliary equation as d square minus m square equal to 0. So we get the roots as d equal to plus minus m. From this we can write the CF as C1. Here we have to continue the sequence of constants, so we can write C5 e raised to mx plus C6 e raised to minus mx, and since the RHS of this equation is 0, so particular integral is 0. So we get the solution for x as only equal to CF. With these two results for t and x, we can write the solution for u, which is nothing but the solution of the given partial differential equation when k is equal to m square. Now we have to discuss the third and the last case for k, that is k equal to minus m square. This case is very similar to case number 2, only the difference of solution for capital X. This procedure for finding the solution of t is very similar to the procedure of finding solution of t in case 2. Now here, after writing the equation in variable separable form, we can integrate both the sides. So we can write the solution as log t is equal to minus m square c square t plus log c7. Applying laws of logarithm, we get the solution for t as t is equal to c7 e raised to minus m square c square t. Now we have to consider second and third ratio to find a solution for capital X. Apply the same procedure as in case 2. Here only the difference of complementary function, as the auxiliary equation is d square plus m square. So the roots of auxiliary equation will be plus minus im. So CF will be obviously C8 cos mx plus C9 sin mx. Again here RHS is 0, so Pi will be 0 and x equal to only CF. Now we have the solution for t and x, so we can write the solution for u as u equal to t into x, that is u equal to c7 e raised to minus m square c square t into c8 cos mx plus c9 sin mx. Now we are having three different solutions for three different values of k. This is for k equal to 0, this is for k equal to m square, and this is for k equal to minus m square. But we have to select the optimal solution out of these three solutions. Since u decreases as t increases, the only suitable solution of the one-dimensional heat flow equation is the solution number 8, or we can say equation number 8. So u equal to c7 e raised to minus m square c square t into bracket c8 cos mx plus c9 sin mx is the stable and suitable solution for one-dimensional heat flow equation. Now using this solution, we are going to find the solution for different particular cases, that is for different particular examples. So in the next lecture we will discuss these examples in detail. Till then, thank you. Have a nice time.